So we discussed certain features which we will require, which we will use further in the coming lectures about the simple nuances of simple statements of the trigonometry, which will be of help to us. And now I introduce to you, so the physical quantities are of two types. One are called scalar quantities and others are called vector quantities. Scalar quantities have only magnitude, like mass, like time, like length. All these quantities are, and many more like temperature, etc., they are scalar quantities. So you can look in the books and you can find what are the various scalar quantities. One thing about the scalar quantities is that they have the same value in all directions. So direction is not a factor in the explanation of scalar quantities. But vector quantities, like we are going to introduce the position vector and displacement vector, the vector quantities have two features. One is the magnitude and the other is the direction. So a vector has two features. Vector has two features. One is its magnitude, that is its absolute value, which is positive, and the other is its direction in space. Direction is a property of space. So one thing what we can say is that we have to specify a vector by its magnitude and also its direction. Now the magnitude can be changed. The magnitude can be made variable and the direction can also change. So a vector changes in three ways. One, you change the magnitude without changing the direction, you change the direction without changing the magnitude, and you change both of them, okay, at one time. So in space, which is three-dimensional in nature, but I'll just take two dimensions like this. Suppose I describe it, as I told you, with the x-axis, with the y-axis, with the minus x-axis here and minus y-axis, minus y, minus x, and we have a point of reference O here, which is for origin, and suppose a point exists here. I call this point as P, and then if I connect O with P, this is a vector where I connect the 2 points O and P, and suppose I call this vector certain vector with a magnitude which is equal to OP and a direction which is like this, which can be described as inclined at an angle of theta with respect to the x-axis, which we take the reference axis here in the xy system. So I can have various points in this space, here and here and here, anywhere, and if I connect, I know the exact position of the particle, of the position of the body, of the position P. Now suppose we just have another vector here, a position vector, which we specify with the help of this line here. Then, now, if I have this vector, I call this vector RP, vector RP, and this I call as vector RQ, vector RQ, like this. Then if from the head of the Q I draw a line to the head of P, then I obtain a vector here which we can say is a vector delta R. Now this is the displacement vector, and the ensuing algebra for the vectors will show that delta R, this RQ plus delta R is equal to P. So RP. So I have RQ plus delta R is equal to RP. I am using the vector sign. Sometimes in the textbooks these vectors are shown with the bold letters, and but when we write, it's always better to use this sign, which is an arrow, starting point, end point, and like this. So you can see that I can write delta R in the simple algebraic manipulation. This can be given as RP, the position vector, the point P, minus RQ, which is the position vector related to the point Q. Now this delta R is called the displacement vector. So what we have done is, we have sort of introduced to you a position vector, position vectors in the simple xy plane, in a planar condition. This could be three-dimensional also, and I am not able to take here the three-dimensional case, but I will show to you how the three-dimensional system also evolves out of the simple mathematics over here. So now I make an introduction to the vector quantities, and let me say that there is a vector which is represented by an arrow, and it has a starting point and it has got an end point, and between them it is a simple straight line which has the magnitude. I can say this vector A, this is, suppose I call this a vector A, which has a magnitude A, vector A, and I show the magnitude with the help of the two parallel lines like this, and the magnitude, it's easy to say that this is equal to A. Okay. So this is A, the magnitude of the vector, but I cannot define the vector A like that. The vector A has to be defined in terms of a direction, and this direction, I can say that there is a vector starting from here to here, and this vector is vector A cap. So when I try to write the algebra of the vectors, I can have a simple representation. I can say that this vector A is equal to A, vector A is equal to the magnitude A multiplied by A cap. I'll show you as to what is an application of a vector quantity multiplied by a scalar later on. But right now you have to say that vector A is defined as the magnitude A into A cap. A cap is a direction vector. A cap is a direction vector. Direction vector, also known as unit vector. For the defined vector, this is a unit vector. So from this equation I can write that this vector A cap, which is our direction or unit vector, okay, this is equal to vector A divided by its magnitude A. And look here, we have the constraint that the unit for the vector and the unit for its absolute value or the scalar value or the magnitude of it, the two units are the same. For example, if this is a velocity vector, then it will be in meter per second, and this will also be in meter per second. So this divided by meter per second divided by meter per second will give you a unit value, and which is just a number. So I am justified in saying that an equation which is obtained like this now is a valid equation, that the unit vector and the direction vector is equal to the vector divided by its magnitude. But some of you can say, as we have been trained, that is it possible to write from this set of equation, this equation, that A is equal to, the magnitude is equal to vector A divided by vector A cap. Now, algebraically it appears to be okay, but I will insist that this is not a possibility. This is something, an equation which we can call absurd, nonsense, idiotic, etc., etc. Why is it that this equation, which appears to be so simple, which we can obtain from here for the vector representation that we have, this is absurd, this is idiotic, this is nonsense, because here itself I am telling you that division by a vector is not defined. Division by a vector, this is a very important point, and particularly for the young brains, vector is not, I emphasize, and then defined, not defined. So something which is not defined has no meaning for us. We don't have an iota of understanding as to what is anything which is not defined. So which is not defined, then this is completely absurd. I emphasize, re-emphasize, emphasize time and again that this kind of a situation cannot arise, and therefore writing an equation like this is idiotic, is nonsense, is absurd, and whatever you want to say by any words that you may choose. So this here we are getting a scalar by a division of a vector by a vector which is not defined. So I define that this equation is absurd, and in any situation this equation is absurd, absurd, absurd. So now let us see what is the scaling of a vector. Okay, so I have taken a vector here, and with this I go to define to you for the vector that we have with the kind of absurdity which I have defined to you, told you that exists. Now suppose I have a vector which starts from the point A and ends up at the point B, and we define this as vector A. Okay. It doesn't matter where it starts and where it ends in the system that we can define as the three-dimensional or two-dimensional space, etc., etc. But allow me to draw another vector parallel to this vector, and starting from another point A prime, ending here at B prime. And it appears to you, and it's true, that this vector from A dash to B dash, this vector is, the length of the vector is twice the length of the earlier vector. So this vector, I can say, if I call this vector as A, I can say that this is a vector A multiplied by 2. Or similarly, if I have a third vector of the same variety which is of a length which is say A double prime, B double prime, and this I call a vector half multiplied by A. So with that numerical example, I am able to tell you that this is the least of these three vectors, and the three vectors, I am saying that the point of start in the three vectors is immaterial, the point of end is immaterial. The only thing is material is the ratio of the three vectors. Here the ratio of this upon this, the ratio is twice. This upon this, the ratio turns out to be 4 times. So it is lengthwise. The other feature is that the three vectors are parallel. So in dealing with the vectors, we make vectors which are parallel to each other, like we'll see in the additional vectors. And another feature that I come to here is two equal vectors. So this vector A I am considering, and then I have another vector of the same species, of the same length. Say I call it A triple dash to B triple dash, but you can see that this vector is also equal to A. So a set of parallel vectors, two vectors which have got the same magnitude when the thing is defined. For example, all of these vectors are displacement vectors. All of these vectors are velocity vectors. All of these vectors are momentum vector. All of these vectors are acceleration vectors, force vectors, or whatever the definition of the vector, in the same set of units and defined in the same plane. Okay. So multiplying a vector, here it turns out to be by a number, here 2, here half, etc., only changes the magnitude of the vector. The direction of the vector is unaltered, unchanged. Okay, like that. Now, allow me to introduce to you how there are two vectors and I add the two vectors or subtract one vector from the other vector. That is, I want to introduce to you what is an operation which has a vector A of this magnitude, vector A, and there is a vector, suppose I call it a slanted vector of a different length but same species, same family, velocity, velocity, acceleration, acceleration, etc., etc. Okay, and these two vectors, they have a starting point and an end point which is the head of an arrow. How do we add them? That is, we want to know as to what is the resultant vector A plus B. The resultant vector which results when the addition is carried out. So what are the ways of obtaining that? So one of the ways is that we redraw anywhere, any starting point. Let me have this as the starting point. The vector A, whatever its length here, and this is the vector A with the magnitude A, etc., whatever you want to say. And then from the head of this vector, I draw the vector B parallel to the original vector B, and I will say that this is my vector B. So the starting point is this one, and once I bring it together, these two vectors, then we have the end point over here. This end point we often call the head, and this point we always call a tail. So if I now connect the vector, the tail of the vector A to the head of the vector B and obtain this line here, then this gives us the sense and the magnitude of the vector A plus B. The condition is that the two vectors should be of the same family, and what results is also of the same family. Velocity, 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 acceleration, 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 force, 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 momentum, 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 whatever. So A plus B, I'll get like this. Now let me introduce to you the vector minus A. Any vector, what is vector minus A? So this is equal to minus 1 times the vector A. So what I told you, what is minus 1? Minus 1, or this minus sign, is 180 degrees angle difference between A and minus A. So if I have this A, this vector is A, suppose here in this case this is the vector A in the x direction, then of course if I draw a parallel vector, a line which is equal in length, but parallel to the first vector, this one, but the direction is changed, that is there is angle. If I bring this vector over here, then the angle between the two of them becomes 180 degrees, which are opposite to each other. Then this vector we can call as vector minus A. So in doing so, if I want as to what is the value of vector A minus vector B, then this vector which was B over here, which is in the original thing it is like this, I can draw a vector parallel to my original vector and call this as minus B, vector minus B. So what I have to do now in this case is redraw my vector A, and from the top of it or from the head of it I will draw a vector in the opposite direction which starts from the head of this vector, and I can show that with an extension of this line and of the same length, and this vector becomes vector minus B. So what I introduced to you in the case of A plus B equal to R, now in this case the resultant vector of vector A plus minus B will turn out to be a vector which again starts from here and ends up at the head of this vector, and this vector becomes A plus vector minus B, which is nothing but equal to vector A minus vector B. So this is one method by which vectors are added or subtracted. Okay, so this vector, if I want to call it vector S, then here it comes the resultant vector S, which is equal to A plus multiplied by minus B is equal to A minus B. This is the simple method of head to tail, tail to head, tail to head. This is one method where in the sequence of A plus B, I take A, then B, then from the head of the B, head of the A, I redraw the vector B, which results in the tail to head system, and this is A to B. Before I shift a bit, I must tell you one thing more, that the positioning of the two quantities A plus B can be done like this. If I take the vector B, for example, I will take the vector B, which is parallel to my original vector B, of the same length, of the same species. This is my vector B, and I will show it to you that you can easily understand. And then from the head of this B, I draw the original vector A parallel to the vector before, then I will get this as vector A. So if I now connect the tail of vector B, the starting point, to the head of the vector A, I again get a vector over here, and this vector becomes equal to, by definition, B plus A without changing the sequence. Okay, and you can see, you can now see, compare this vector with this vector, and you find that the two vectors are in the same direction, and the two vectors are the same species, and the two vectors have got the same magnitude. So I can say that B plus A is equal to A plus B. So what is there is that this kind of a relationship is, in mathematical terms, commutative. What is commutative? It can commute, that B can come to the position A and A can go to the position B, and the result remains unaltered, unchanged. So one of the things that is there is B plus A is equal to A plus B. Now these things I again introduce to you for the vector quantities that we have with another rule, another law. This was the tail to head procedure, and the other procedure is again very interesting, very simple, which you can understand. Okay, now what again I am going to do is that I am going to take a reference point here and draw my vector A of the same magnitude parallel to the original vector. And if I say that the magnitude of this vector is A, allow me to write this over here. And then from the same point, again I shift this vector B to the same point, and I obtain the vector B here, parallel to the original vector B, and I get the two adjacent lines which make a triangle over here. An angle over here. And this angle I can say, well, okay, this angle is equal to theta. Now what we do is, I can shift this vector A here parallel to itself and starting from this point. So I have, again, allow me to draw this vector, and it's not unreasonable to call this vector again as vector A. Okay, and similar exercise I do by from the head of this to head of this, and again because it is parallel to the vector V, so I write this as vector B. So very interesting. The interesting thing is that this figure which we get over here, this line is parallel to this line and this line is parallel to this line. So the figure that we obtain over here is a parallelogram. Okay, the figure that we get is a parallelogram, and the parallelogram has a starting point. From this point there is a diagonal from this point, so this point is a diagonal. Now the diagonal of this parallelogram I can write from the previous relation that I introduced tail to head system. This appears to be B plus A here, B plus A, and if I go like this, then I have a vector A, this was there was a vector A here, this was only magnitude A. So anyway, so this now becomes equal to the same thing. I can say that this is vector A plus vector B, vector A plus vector B, and this is called the parallelogram law of vector addition. So you can see that in using this parallelogram procedure to obtain the vector A plus B or vector B plus A, which are equal to each other, we established that the commutative law, where we can exchange the position of the two vectors, is valid. Now, it will be interesting to argue that if I have vector A minus vector B, so let me take this, take you, and you can make several things. You have got a paper, you have got more liberty than I have. This vector becomes equal to vector minus B. So if I add them together, then what do I obtain? I obtain, or we obtain, a vector which is like this. And see, if I shift it parallel to this, then I'll get a vector like this. A vector, I'm going to get a vector like this, which is the other diagonal of the parallelogram. And here, allow me to draw the line here also, and I minus B and A minus B. So in a nutshell, with the help of this parallelogram which I have drawn over here, the diagonal, this one, gives us A plus B or B plus A, and this diagonal here gives us A minus B. So with that, I take it off. I think I have been able to introduce these vectors, and there are many things which I have deliberately not done for you, because my purpose is not to tell you the vector quantities, etc., just to introduce them so that we can. So I have told you about the scalar quantities, the position vector, the displacement vector, about the vector quantities, equal vectors, unequal vectors, you can see. Of course, I told you that if the two vectors A and B are equal to 0, A and B are equal to each other, so A minus B will be equal to 0, but still we say that in the 0 vector we have a 0, but with the vector sign which has got magnitude equal to 0, but it has a direction which has to be defined by the rules of vector addition, etc. Now, I make use of, I told you if the vectors are in the same line, linear vectors, if they are in the same plane, they are coplanar vectors. Okay, addition and subtraction, the two method, head and tail, and this is the parallelogram method. Let me write, and let me parallelogram. Gram means the figure of parallels. So here, and of course, I'll just introduce to you what you used to have, the resultant square. One of the things, parallelogram, law of vector, laws of addition, etc. So I'll say that if we have got two vectors, P and Q, with magnitudes P and Q respectively, the variety of course is the same: force, velocity, acceleration. Then in the parallelogram law of vector additions, we have the resultant, and that equation turns out to be equal to, the resultant square is equal to P square plus Q square, which we can prove geometrically also, and we'll have the occasion P square plus Q square plus 2PQ cos of theta. cos of theta, where theta is the angle between the two vectors A and B. We will have occasion to discuss this again, but this equation I take from the book that I had, and we used to do an experiment also on this. R square is equal to P square plus Q square plus 2PQ cos theta in our intermediate college classes, and this equation is right from the book of Basu and Chatterjee. Okay, later on other books they have different descriptions. So without going into the details etc., I'll just introduce to you the displacement vector again. Okay, I'm sorry, the position vector again. So allow me to introduce the position vector, the displacement vector, etc. Now I will straight away go to the definition of the unit vectors which I defined before, but I will draw the space axes, and as I said in the board, you can see that this is 90 degrees, and this axis, this is x, this is y, and this is z. The three axes. I can rotate these axes. There is something very interesting which I want to share with you here, that suppose I put my axis x over here, then my axis y will come here and axis z will come here. If I put my axis z over here, then this will be my axis x and this will become my axis y. How we go? We can rotate this and obtain that, but before that I'll tell you that this is, again I emphasize that this is also 90 degrees between the y-axis and the z-axis, that the angle over here is 90 degrees, and between this and this, the angle between the two of them is also 90 degrees. They are mutually exclusive vectors. Now, why are they mutually exclusive or mutually perpendicular vectors? They are independent of each other. It's a very simple algebra of trigonometry. Suppose I take a vector, anything which is defined with respect to this theta, and I said that if this is a vector A, the magnitude over here, the vector A is like this, I drop a perpendicular from the head of this vector onto the base here, and then this is the base, this is the perpendicular, and this is the hypotenuse. Now, as I reduce the value of theta to 0, approaching 0, so what will happen? What is going to happen is that the base is going to be approximately equal to the hypotenuse. So if theta tends to 0, the base tends to be equal to the hypotenuse. And therefore, base upon hypotenuse is the cos theta, and cos theta turns out to be equal to n. Cos theta approximates 1. So look here. What happens is that if I reduce the value of theta, and this goes on reducing like this, ultimately the value of the perpendicular becomes approximately equal to 0. The sine theta for that 0 value becomes equal to 0, but the cos theta becomes equal to this, and the result part, as I said, that AX AX is equal to, this is AX, in the X direction, this is equal to A cos of theta, which approximately becomes equal to A itself. So when theta tends to 0. See, look here, this is the beauty of it, that as this, so the dissolved part in this direction is equal to 0. The dissolved part in this direction will be equal to 0. So AY component, I can say, therefore, with the help of this, AX is approximately equal to or equal to AY, the Y component along the y-axis, this is approximately equal to 0 or 0, and AZ in the Z component is also approximately equal to 0, and therefore there is, if there is a vector along the x-axis, it has no component along the y and z. If there is a vector along the y-axis, it has no component along the z and x. And if there is a vector which is along the z-axis, it has no component in the x direction or y direction. Look here, I re-emphasize, I had the axis drawn as x, y, z. X, y, z. And then, this direction is x, y, z. So how do we go? We go like this. We go anti-clockwise. And there is a positive rotation of the axis in the anti-clockwise direction within the axis, and this I can show to you here. If you allow me, then I'll use my left hand and I say that this one is my x-axis, this one is my y-axis and the piece of paper that you have, and this is, here you can see that the x-axis, the y-axis and the z-axis. And if I turn them like this, you can see that this becomes my x-axis, this becomes the same, becomes my y-axis, and now the z-axis, etc., etc. You can do with the help of a book, and you can show this thing. So, to sum up right now, and in an hour's time, I'll show that there are position vectors, there are unit vectors in these directions perpendicular to each other, and these vectors I will introduce to you as the vector I cap, vector j cap, and vector k cap, where the magnitude of each of them, vector I cap magnitude is equal to 1, the the direction vector j cap is also equal to 1, and the position vector, the unit vector or the direction vector k cap is also equal to 1. So I cap, magnitude of I cap, magnitude of j cap, magnitude of k cap, they are all equal to 1. And in the next lecture, which I will take up shortly, I will show to you as to how a vector r can be written as. Whether this vector is a position vector, I can write this with its components as the component x, which is a scalar, I cap, plus the component y, j cap, plus the component k, component z, k cap, like this, where this is a variable. This is a variable. This is a variable. And this is a variable. But what are invariants? What are not changing? They are I, J and K, which have fixed directions and fixed values, what we will obtain. So I will start in my next outing with this thing. Then I'll give to you what is delta R. Like this, I can say that this is delta X, I cap plus delta Y, J cap plus delta Z, K cap. Of course, once again, I can say that this is the displacement, this is also the displacement in the Y direction, in the Z direction, this is the total displacement, etc. And similar equations we can obtain for velocity, acceleration, force, etc. etc. So we'll look into it after the break, inshallah, today itself. Bye for now.